Hello students, welcome back to my channel once again. Students, whoever is watching for the first time, please subscribe the channel and don't forget to like the video and also share with your friends. Okay, so this video, by looking at the thumbnail, you must have understood the topic for today's video is Debye Huckel Onsager Equation for strong electrolytes, which is a very important question from electrochemistry. Okay students, so shall we learn, or are you all ready to know what is Debye Huckel Onsager Equation for strong electrolytes? Yes students, you all please I'm telling you that its full notes is there in this video. Okay, so for your examination point of view, you can note down all the points in your notebook or take the screenshots and you can directly prepare and write it in the exam. Okay students, you need not prepare notes again. So complete notes of this topic I am giving you in this video along with the explanation. Okay students, shall we start? Right. So what is this Debye Huckel Onsager equation? And this is for strong electrolytes only. Okay. So Ostwald, you all know students, right? Ostwald dilution law we have studied, right? Now this Ostwald, he calculated alpha. What is alpha students? It is nothing but degree of dissociation. He has calculated degree of dissociation, that is at alpha, for different electrolytes at various dilutions. Okay. So he changed the concentration at different dilutions. He calculated degree of dissociation alpha and also dissociation constant K for different electrolytes. Okay students, he has taken different electrolytes at different dilutions. He has calculated alpha, degree of dissociation and also K. Okay, now alpha of a weak electrolyte is calculated as follows. That means with this expression, degree of dissociation of a weak electrolyte can be calculated. Okay students, so how? Alpha is equal to lambda V by lambda infinity. Okay, you all know lambda is equivalent conductance and lambda V means equivalent conductance at dilution V. Okay, at any dilution. Whereas lambda infinity, you all know that it is equivalent conductance at infinite dilution. This is at dilution V and this is at infinite dilution. So with this alpha can be calculated for a weak electrolyte. So what did he try to understand by calculating degree of dissociation and K for weak electrolytes? It was found that K was constant for weak electrolytes. That means at any dilution he is getting the same value for different electrolytes at different dilutions. So K value was found to be constant for weak electrolyte students. Okay, and it is not the same for strong electrolytes. Okay, so when he calculated K, it was found to be constant for weak electrolytes. In the case of weak electrolytes, it's remaining the same. Whereas for strong electrolytes, it is not remaining the same. Okay students, this is what Ostwald could find from his experiment. Now according to Arrhenius, we all know that we have studied dissociation of an electrolyte increases with dilution. Okay, so as you dilute, the dissociation also will increase. So as dilution increases, dissociation of the electrolyte also increases. Okay, and as dissociation is increasing, conductance of that electrolyte also increases. Okay, so on dilution we can say dissociation increases and also conductance of the electrolyte increases. This is according to Arrhenius. This we have learned from Arrhenius theory. Okay. Now, this statement is also correct in the case of weak electrolytes but not in the case of strong electrolyte, students. Okay. So, 2 points we have learned here. K was found to be constant in the case of weak electrolytes but not in the case of strong electrolytes, and dissociation and conductance increasing with dilution. This is also correct in the case of weak electrolytes but wrong in the case of strong electrolytes. Okay, correct in the case of weak electrolytes and wrong in the case of strong electrolytes. We will try to understand the reason for this. Okay, students. Strong electrolyte. Any strong electrolyte you take and add some water, immediately on adding, that is at the first dilution, or we can also call it as the moderate dilution, strong electrolytes are almost completely dissociated. It's not like on dilution dissociation is increasing. First and foremost dilution itself, the strong electrolytes are ready to dissociate completely. Okay, that means at the first dilution itself, how many number of ions it can produce, those many number of ions will be produced at moderate dilution itself. There is no chance of increase in number of ions on dilution. Okay, but conductivity increases with dilution, students. Try to understand the difference. There is no chance of increase in number of ions with dilution, but there is a chance of increase in conductivity with the dilution. Okay. So, the reason for this, why this is correct in the case of weak electrolytes and wrong in the case of strong electrolytes means, on dilution dissociation is increasing is correct in the case of weak electrolytes but not strong. Why? Immediately when you add water, that is at first dilution itself, maximum number of ions will be produced. That means it can be completely dissociate. Okay. But conductivity increases with dilution. Okay. Mark this point, students. Fine. Now, due to the complete dilution, almost complete dilution at moderate dilution itself, degree of dissociation cannot be determined by the ratio lambda V by lambda infinity as in the case of weak electrolytes. Okay. In the case of strong electrolytes, alpha cannot be determined using this lambda V by lambda infinity, students. Why? Because see, it's not like on dilution degree of dissociation is not increasing. At the moderate dilution itself, it is getting completely dissociated. Therefore, now lambda V by lambda infinity, this ratio can be called as conductance ratio but not degree of dissociation. Am I clear, students? Okay. This is in the case of strong electrolytes. Now, as strong electrolyte is completely ionized at moderate dilution itself, lambda V and lambda infinity should be equal now, students. At infinite dilution, how many ions are there? At first dilution itself, those many ions are being produced. Okay. So, lambda V and lambda infinity should be equal in the case of strong electrolyte. But actual practice, lambda infinity is greater than lambda V or lambda V is less than lambda infinity. Okay. So, what is the reason for this abnormal behavior of strong electrolytes? Okay. So, in order to explain this abnormal behavior of strong electrolytes, Debye and Huckel, they proposed a theory, Debye Huckel theory, and they gave various reasons for the deviation of strong electrolytes. Okay, students, here again, as strong electrolyte is completely ionized, lambda V and lambda infinity should be equal. But in practice, lambda infinity is greater than lambda V, or in some textbooks you will find lambda V is less than lambda infinity. Both are same, students. This abnormal behavior of strong electrolytes was explained by who? Debye and Huckel. That is Debye Huckel theory, and they gave the following reasons for deviation. Let us have a look at the reasons for deviation, students. First one is asymmetric or relaxation effect, students. Okay, what is that ma? Asymmetric effect or relaxation effect. What do we understand under asymmetric or relaxation effect? Students, you all know that in a solution there will be two ions, positive and negative ions. Okay. Now a positive ion will be surrounded by negative ions, or a negative ion will be surrounded by positive ions. Okay. So that the same I have written here. Each ion in a solution will be surrounded by an atmosphere of oppositely charged ions, which we call it as ionic atmosphere. For example, a central positively charged ion, okay, it will be surrounded by an atmosphere of negatively charged ions. So, as long as no electric field is applied, that means when there is no electric field, the ionic atmosphere will be symmetrical. That means it will be uniform around the central ion. When, students? In the absence of electric field. And the force of attraction also exerted by the ionic atmosphere on the central ion will be same in all directions, and therefore net force of attraction becomes 0. Okay, this is all in the absence of electric field. Now, when the electric field is applied, the same situation will not be there. The situation changes. It becomes different. What happens? Central ion moves in one direction and the ionic atmosphere moves in the opposite direction. So where are they going? Central ion moving towards which direction? Ionic atmosphere moving towards which direction? Below I have given a small diagrammatic representation, students. Okay. First one, you can see central positive ion surrounded by the negative ions, atmosphere of negative ions. Okay, this is the ionic atmosphere. This is in the absence of electric field, students. Okay, now, so this is we call it as symmetrical ionic atmosphere in the absence of electric field. Below I have written, see, students, symmetrical ionic atmosphere in the absence of electric field. Now, right side figure. Now, the electric field is applied. Okay. So, this positive ion is attracted towards the negative electrode, and the negatively charged ions, they are being attracted towards the positive electrode. I have put all the arrows, students. Look here. This arrow this side and all these negative ions arrows this side. Okay. So now what is happening? The situation is becoming different. Central ion moving towards this electrode and all the negative ions, that is the ionic atmosphere, is moving towards the positive electrode. So now it has become asymmetric. Now it's not symmetrical. Therefore, you mention asymmetric ionic atmosphere in the presence of electric field. Okay. So presence of electric field, absence of electric field. How is the position of the ions in a solution? We have understood, students. Explanation of the diagrammatic representation. Put it in the form of a sentence. Positively charged ion moves towards cathode and the ionic atmosphere moves towards anode. The symmetry of the atmosphere is now lost and it becomes asymmetric. This is in the presence of electric field, students. Okay. In the presence of electric field. Now, this situation, that means electric field, when it is applied, there will be more number of negative ions behind positive ion than in front of it. Okay. As a result, what happens, students? It experiences net attractive force in the back. That means they will be pulling the positive ion in the backward direction. It experiences a backward pull. What happens by that? Consequently, the central positive ion experiences a retarding force. Okay. That means a backward pull which tends to drag it towards backward direction. Okay. Why? Because there are more number of negative ions behind the positive ion. When, students, this is in the presence of electric field. Because of this, it's being pulled backward because as it experiences a retarding force. So therefore it cannot move freely. Because of that, what happens? The movement of the ion is becoming slow, is slowed down. Okay, now the slowing down of speed of the ion due to asymmetry of the ionic atmosphere is called as asymmetric effect, students. Okay, so you understood asymmetric effect? Okay, the movement of the ion in the presence of electric field, as it is experiencing a retarding force, it will be dragged towards backward direction. Hence its movement becomes slow, and therefore the decrease in the speed of the ion due to asymmetry of the ionic atmosphere, we call it as asymmetric effect. Okay, now as the central positive ion, now it is moving out of the ionic atmosphere, students. Okay, so what happens now? There in a similar ionic atmosphere, which is a new one, it's being formed around the central positive ion. Okay, and in other words, we can say as the ion it is moving towards the opposite electrode, the old ionic atmosphere, what is happening, students? It's getting decayed and a new atmosphere is rebuilt. Okay, students, hope you understood this concept, right? Now, but between the decay of the old ionic atmosphere and the formation of the new atmosphere, new ionic atmosphere, there will be some time lag or time gap, students, which we call it as relaxation time. Okay, what is that, ma? See below. However, there is some time lag between the decay of the old ionic atmosphere and formation of the new ionic atmosphere. During this relaxation time, the central positive ion, what is happening? It experiences a backward pull by the old ionic atmosphere. Okay, as I told you here, students, during this relaxation time, the central positive ion, it experiences a backward pull by the old ionic atmosphere, and hence the movement is becoming slow or it's retarded. Hence this is also called as relaxation effect. Okay, so the effect has two names, students, asymmetric or relaxation effect. Asymmetric effect is slowing down of speed of the ion due to asymmetry of the ionic atmosphere is asymmetric effect, and in the relaxation time, the central positive ion, as it is experiencing a backward pull by the old ionic atmosphere, its movement will becomes slow, and hence this is called as relaxation effect. Okay, this is the first reason, students. Second reason, electrophoric effect. Second reason, electrophoric effect. Put the side heading, students. Okay, now this is the other factor which is responsible for the slowing down of the movement of ion is. Another factor which slows down the movement of the ion. Previous one we have seen relaxation effect. Now the second factor is tendency of the ionic atmosphere with its associated solvent. You might get a doubt, ma'am, where from the solvent molecules are coming. See, students, we are talking about the ions, means it is in the form of a solution, right? So in the solution we know there will be solvent molecules. So the tendency of ionic atmosphere with its associated solvent molecules, what they will be doing? It will be moving in a direction which is opposite to that of central ion moving with its associated solvent molecules. Students, here the ionic atmosphere will be associated with its solvent molecules. Central ion will be associated with its solvent molecules. Okay. Now this ionic atmosphere along with its solvent molecules will be moving towards one direction, and the central ion with its associated solvent molecules will be moving in another direction. For example, a cation with its associated water molecules moves in a direction opposite to that of negative ionic atmosphere moving with its associated water molecules. Okay, so cation with its associated water molecules, negative ionic atmosphere with its associated water molecules. One going towards this side, one this side. Okay, now because of this opposite directions, we can say that there will be counter currents. Counter currents means what? Opposite currents within the solution, and because of which the movement of the ion will become slow. This slows down the ion, and this effect we call it as electrophoric effect, students. Okay, now taking the above effects, what are the above effects? Asymmetric effect and electrophoric effect. Debye and Huckel, they derived a mathematical expression in order to explain the variation of equivalent conductance with the concentration. Okay, students, underline this point. They derived a mathematical expression for the variation of equivalent conductance with concentration. And this mathematical expression derived by Debye and Huckel was further improved by another person called as Onsager, and hence it is known as Debye Huckel Onsager Equation. Debye Huckel Onsager Equation. Now what is Debye Huckel Onsager Equation, students? Look here. For an univalent electrolyte, for example NaCl, KCl, students, they will be, see look here, what is univalent electrolyte I have written here. One in which each ion has a charge of 1. So Na plus Cl minus, plus 1 minus 1, K plus Cl minus, plus 1 minus 1. And when dissociated, 2 ions are produced. Okay. Now for an univalent electrolyte, the equation for a particular solvent at a given temperature is given as follows. Lambda V equals to, equivalent conductance at dilution V is equal to equivalent conductance at infinite dilution minus A plus B into lambda infinity into root C. Okay, students, this is Debye Huckel Onsager equation. Now you know these two terms. What are A and B? A and B are constants and they represent electrophoric and asymmetric effects, and C is concentration in gram equivalent per liter. Now A and B values depend on nature of the solvent and temperature. They are given by the following relationships. Okay. So A is equal to 82.4 by dt to the power half into eta, and B equals to 8.2 into 10 power 5 by dt to the power 3 by 2, where D is dielectric constant, T is absolute temperature, and eta is viscosity of the medium. Okay, students, there is no derivation for this. Just we will be writing the equation. Okay, written, students. Now we will give the conclusion from this equation. What to write on the conclusion, students? As concentration decreases. What is meant by concentration decreases means when the solution is being diluted, the magnitude of the term in the equation A plus B into lambda infinity into root C decreases. Okay. When concentration decreases, this term also decreases, the magnitude of this term decreases, and lambda V value increases. Okay. Now, when this concentration is becoming 0, that means at infinite dilution, lambda V slowly approaches lambda infinity, students. Okay. So this is what you will write as a concluding sentence for Debye Huckel Onsager equation. Okay, students, this is a very important question. Please try to understand. Okay, then write down the points in your notebook and then it will be easy for your exam. Okay, students, meet you in the next video with a new topic. Take care. Bye-bye.